Okay, so this is a brief lesson on some of the finer points of U5 and 2 types of bonding. The first thing I want to call your attention to is why atoms bond. And the reason why I want to call your attention to this is because they tend to bond to create a more stable arrangement of electrons, which means that they are trying to lower their potential energy. So when they're trying to lower their potential energy, they're trying to create electron stability around the nucleus of the atom. And the general rule of thumb is that all atoms want to have 8 valence electrons. They all want 8 in their highest energy level, or their valence electrons. There is one major exception to this. Actually, there's a couple major exceptions to this. Hydrogen would like to have 2. Wants 2 valence electrons. And then helium wants 2. And lithium wants 2. Now, I'm going to show you why that's the case in a couple of minutes, but the reality is that hydrogen wants 2 valence electrons. Really, it wants none, but we say that it wants 2. Helium wants 2 valence electrons, and lithium wants 2 valence electrons. So this part right here is going to become important for the last few pages of the notes, so I'm going to kind of skip ahead to that in a moment here now. Okay, so how do we know if a bond is ionic or covalent? Because we just learned about the fact that ionic bonds transfer electrons completely from one atom to another, and covalent bonds share electrons between two atoms. And in order to get to that reduced stability, or to become more stable rather. So it has to do with something called electronegativity. And on your periodic table, like we have it's like mercury, and then we have that it's element number 80, and then it's Hg, and then it's 200.59, and then we have, I think it's 1.9 right down here. That's your electronegativity value, and that's where you get it from the periodic table. But the reality is that there's these cutoffs that kind of like distinguish between whether a bond is ionic or covalent, and it's based on how much of a percentage the electron is being shared versus the electron is being transferred. So the way that we look at it is this chart here. And in the notes, like on Google slide deck, this is colored a little bit differently. Like I believe this is blue and this is more of a green. But the reality is that the larger the difference in electronegativity, remember difference means we're subtracting, the more ionic the bond is actually going to be. So if it is a large electronegativity value, a large electronegativity difference value, we are able to say that the electron is transferred completely. And if it's a very small electronegativity value, we would say that it's sharing, and depending, the type of sharing would be whether it's polar covalent or non-polar covalent. So going back to these cutoffs here, if the electronegativity difference is between a 0 and a 0.4, it's non-polar covalent. If it's between 0.5 and 1.7, it's polar covalent. And if it's 1.8 or greater, we would say it's ionic. And at this point, the electron is transferred. Here, the electron is shared equally. And here, the electron is shared unequally. Okay, which is basically what's written here. So we have a mostly ionic between metal and a nonmetal. Usually metals are on the left side of the periodic table, and nonmetals are on the right side of the periodic table. Then we have the unequal sharing between, which is polar covalent, which occurs between 2 different nonmetals. And then we have equal sharing, which generally seems to occur between 2 of the same nonmetals, although sometimes it's not always just 2 of the same, but a lot of times that it is. So let's take a moment to take a look at how we calculate an atom's electronegativity. So I went through the process of finding these elements on the periodic table and grabbing their electronegativity value from the lower left-hand or right-hand corner of the periodic table box. So to calculate the electronegativity difference, the E and D, I'm going to take the iodine's 2.5 minus bromine's 2.8, and I'm going to put that in absolute value so that it comes out with positive or no charge, and I'm going to get that this is a value of 0.3. Right? So if I go back to my cutoff, it's a 0.3, which means it's nonpolar covalent. And then the question is, which atom is more negative, meaning more electronegative, or where the electron spends most of its time? And the answer has to do with the larger electronegativity number. So bromine, even though this is shared mostly equally, bromine has a little bit more of a pull than iodine does. So that means the electron is going to be pulled more towards bromine because it's more negative. Okay, so then we have 2.5 for carbon and 2.5 for sulfur. So I'm going to take 2.5 minus 2.5, and I'm going to get 0.0. And again, going back to my chart, 0.0 is nonpolar covalent, so nonpolar. Now in this case, both of the electronegativity values are exactly the same, so the electron is shared equally, so the more electronegative atom does not apply. It's not applicable. Now I have 0.9 minus 3.0. 0.9 minus 3.0, I believe, is 2.1. Okay, so if I look at this, take a look here, and I see it's greater than 1.8, so that means that this is an ionic bond. And as a result of that, the more negative atom is the one with the larger electronegativity, which is going to be chlorine. That means that the electron is going to be pulled from sodium to chlorine. Here we have oxygen, which is 3.5, hydrogen is 2.1, and we're going to subtract that, and I believe it's 1.4. 1.4 falls in the range of polar covalency, so this is going to be polar covalent. And again, the larger the electronegativity value, the stronger the pull the electron is toward that atom, so that means the more negative atom is going to be oxygen. And lastly, we have 2.5 minus 0.7, which I believe is 1.8. And this falls right on that line, that 1.8, so this is going to be ionic. And again, the larger electronegative value is 2.5, so it's going to be sulfur. Okay, so you should be able to use the periodic table to help you come up with these values. Again, they're in the lower right-hand corner, and then you should be able to go ahead and be able to answer questions like what type of bond is present.